Welcome to Mr. Frolic's physics classes. In this video, we're going to discuss Newton's second law. Hello there. Today, we are interested in talking about what will make an object change the way it's moving. So, first, let's just consider a ball sitting on a horizontal floor. If I want that ball to move, okay, let's say that's initially at rest, and I want to make this ball move, I need to kick it. I need to exert a force on the ball. Otherwise, it's going to stay still. So a force is required to make this ball change its velocity. And when the ball changes its velocity, I'm going to have actually an acceleration. Acceleration is the quantity that measures how fast velocity changes. So what we want to develop in this video lecture is a relationship between an applied force and the acceleration of the object, and all of the possible implications that come through there. We'll watch an experiment that I recorded a couple years ago, in which we're going to try to establish a relationship between applied force and acceleration. This experiment was done in 3 steps. So let's see step number 1. So we will study the relationship between the applied force on the cart and its acceleration. To measure the applied force, we will apply a force here at the hook of a force sensor that is mounted on the cart. And to measure the acceleration, we will use a motion sensor to map this acceleration. And the data is going to be treated, and we're going to see it here in the graph. So now, coming back here and start the collection of data points. This is now, I'm just plotting, and we can see the graph over there. And now we have in here, the linear fit was a linear function, a slope of 0.62 units we're still going to discuss, an intercept of basically 0, and a correlation of 0.99. This tells me that this data is actually basically a proportional data. So the relationship between force and acceleration seems to be directly proportional. Experiment 1 essentially gives me a graph of force versus acceleration that is very well described by a straight line passing very close to the origin. Notice the information that we have here, what's important. A slope of 0.62 units, a correlation of 0.99, which is almost a perfect straight line, and a vertical intercept that is roughly 0.2, very small. Let's now watch the second experiment where a ½ kilogram mass is added to the system. Let's now see what happens if we add a ½ kilogram mass or 500 grams mass to the cart. So here's the mass applied at the cart. I'm going to run the collect and pull the cart back and forth, and we see the data being collected on the computer. And we get in here now still a very strong correlation of 0.99, a linear function with a basically 0 intercept, so it's directly proportional that we see in here, and the slope has now increased to about 1.17 units. Experiment number 2, with an extra ½ kilogram mass on top of the system, still gives me a very close to a straight line graph for force versus acceleration. A correlation still of 0.99, so a strong indication of that, and a vertical intercept of negative 0.2, still very small. Notice that the slope has increased to 1.17 units. So as I went from the first system to the second system, my slope has increased from 0.62 to 1.17, an increase of about 0.51 units. Well, now we're going to do a third experiment where another half a kilogram of mass is added to the top of the system, and everything else is repeated. Notice it gets a little bit trickier to be pulling back and forth because now the masses can slide one on top of the other. And let us see the results. Finally, let's see what happens if we add a second half a kilogram mass on top of the first one. So clicking collecting here and collecting our data. I need to be gentle now because the masses would actually be sliding on top of each other if I am not gentle. And our correlation was not as good, but the masses was sliding a little bit. My slope goes up to 1.62. The y-intercept is basically 0, and we still have a directly proportional between force and acceleration. Experiment number 3 gave me the very same force versus acceleration graph. The same shape of the graph, a correlation of 0.98, well, slightly less than what I had before, but we need to admit it was harder to keep the masses all moving together. A vertical intercept still of about 0.18, negative 0.18, which is almost 0, and finally a slope of 1.62 units. Notice that from the first to the third, I actually add 1 full unit when I added 1 full kilogram of mass on my system. These results here allow me to actually write a mathematical equation, which the computer actually is providing me, where I say that force equals some slope multiplied by acceleration plus a vertical intercept. And this vertical intercept here, so far, is almost 0. Let's think a little bit about the meaning of this vertical intercept. It would be an amount of force that I need to apply on the system all the time to have absolutely no acceleration. So coming back to my original ball, it would be as if for this ball to just stay still, I still needed to keep applying some force on it, which in my opinion does not make that much sense. So I would rather think that this vertical intercept is either some experimental error coming from me, the way I was doing the experiment, or maybe because it's always roughly the same, some kind of rolling friction that has not been accounted in here. After watching those videos, let's put all of those ideas together and try to come up with a mathematical relationship between force and acceleration. First, let's look at the system. I have the cart and the applied force. This applied force is a force that is actually being measured. So this is the measured force on my system. But that's not the only force acting on the cart. I also have acting on this cart a gravitational force, or the weight of the cart, contact forces on the wheels, and some small rolling friction, although that rolling friction reverses direction back and forth as I'm moving the cart. These forces here cancel out, and this rolling friction, which is almost 0, was actually accounted for in that small little vertical intercept that I said, let's just at this point ignore. So basically, this applied force is almost actually the sum of all of the forces, or what we call the net force on my experiment. The sum of all forces is actually the first force plus the second force plus the third force plus all of the forces. It's just an operator saying add all of the forces that are acting on your system. I would stick more with the name net force. The results from all of our 3 labs allow us to actually state that net force is directly proportional to acceleration. From a math perspective, I can easily write then that net force equals a constant proportionality, K, multiplied by the acceleration, A. Now, this constant proportionality, let's remember, is the slope of the force versus acceleration graph. And what we saw is that every time we add half a kilogram of mass to the system, the slope of the system increased by half a kilogram. This is evidence that this slope actually measures the mass of my system. And if the slope really measures the mass of the system, I can then rewrite my equation for force and acceleration this way here. Net force equals mass times acceleration. And this now is the mathematical form for Newton's second law of motion, one of the most important equations or laws in physics or in the whole scope of science. First observation is about units. In international units for force, is Newton. Okay? For Isaac Newton. And 1 Newton of force is the force that applied to an object of mass 1 kilogram makes it accelerate at a rate of 1 meter per second squared. So we have that 1 Newton is equivalent to 1 kilogram times meter per second squared. Second observation is about mass and acceleration. If, from Newton's second law, I solve this for the acceleration, what we have is that keeping the net force the same, constant, the bigger the mass, the smaller the acceleration, and vice versa. Or that acceleration is inversely proportional to mass. Notice that I could reason somehow that the net force is something that is disturbing the system, trying to make it change. Mass is a resistance to change. The more massive my system is, more it resists change. And acceleration is the response, is the amount of change I get. Okay? So more resistance, less response. Less resistance, more response. Another thing I would like to discuss is this here. The way we did our lab, the independent variable was actually the force. I control the force applied to the force sensor. So the independent variable was force. And the dependent variable was the acceleration. That was the response to the system offered to me. So in some sense, I should actually have graphed this as acceleration versus force. And some people write Newton's law first as acceleration equals force over mass. I did not do this way. I did reversing. Really because, one, I already knew how form I want it for the law, but also number two, if I graph acceleration versus force, my slope is going to be the reciprocal of the mass, which is not that useful for us. For us, it's better graph in a way that the slope is going to be straight to mass. That's the only reason. My next observation is going to be with respect to force and acceleration in this way. Notice that mass is a scalar, is a number, and that number is always positive. So what I have is that I'm multiplying the vector acceleration by a positive number, and I get a vector mass. And that mass is always going to be in the same direction of the acceleration. So if by any chance my system has an acceleration like this, I know before I even start that my net force, well, is going to be in the same direction. And I'm going to tell you that I've been a little bit sloppy in one thing here. I should have written net force here and net force here. Please never write F equals ma. That is confusing for students. Always write net force equals mass times acceleration. So coming back in here, my conclusion is that the net force on a system is always going to be parallel to the acceleration. And this is quite useful when you start solving problems that involves forces in more than one direction, in trying to identify which force is going to be the more intense, which direction is the total force, and this kind of stuff. The next observation on my list, number 4, is just a graph of net force versus acceleration. And this graph here should be a straight line, and the slope of this graph should be the mass. Observation 5. Relationship between mass and weight. Let's consider an object that is falling on free fall. If this object is falling on free fall, we know that its acceleration down is equal to the acceleration due to gravity. If I apply Newton's second law to this object, net force equals mass times acceleration, and now I substitute the acceleration to be the acceleration due to gravity, net force equals mg. But the definition of the object on free fall is that the only force acting on the object is the gravitational force. And if the only force acting on the object is a gravitational force, then the net force on the object is going to be the gravitational force. And then I can write in here that the gravitational force equals mass times the acceleration due to gravity. Okay? And I think that at this point, I should talk a little bit about the relationship between mass and gravity. So let's think about it this way here. Let's consider the surface of the Earth and little Johnny here at the surface of the Earth. And Johnny has a mass of 50 kilograms. This means that there are roughly 50 kilograms of stuff making his body. This is basically what it means. It just tells me how much stuff makes his body. Now, if Johnny hops on an airplane, and then he's flying on this airplane, Johnny is still the same person. He hasn't changed at all. And if he's the same person, then that means that his mass is going to be the same 50 kilograms. Now let's say that Johnny actually, instead of being on an airplane, was on a spaceship that took him to the moon. And here's Johnny at the moon. And this trip took, I don't know, a day or two perhaps. I don't really know what technology we're going to have at that time. If service is as good as it is in airlines nowadays, he hasn't eaten much anyways. So he's going to be the same person in the moon that what he was on the Earth. So his mass would still be 50 kilograms. Even if Johnny goes out on outer space, some fancy spacecraft, whatever, and he's far away from any planet, from anything, he's still going to be the same person. So his mass is still going to be 50 kilograms. We see that the mass is a property of the object. It does not change unless the object itself is changing. Now let me add one more thing in here. It measures the inertia of a system. Inertia is a word I'm using for the first time now, and basically it is a property of mass to oppose changes in its state of motion. So a large inertia means a system or an object that will not want to change its state of motion. The more inertia, more resistance to change. Less inertia, easier it is to change. And notice that mass in the International System is measured in kilogram. Now, force, on the other hand, is the interaction between your mass and the gravitational field on the place you are. So, for example, on the surface of the Earth, where gravity, I'm going to round up to 10 meters per second squared, so Johnny's weight or gravitational force would be 500 newtons. When Johnny is on an airplane, we know that the acceleration due to gravity will decrease with the increase in altitude. And so let's say that on this airplane here, his gravitational force now is going to be maybe 495 newtons. Okay? When Johnny is at the surface of the moon, the gravitational force would actually be 1/6 of that on the Earth, because the gravitational attraction of the moon is 1/6 of that on the Earth. And then the gravitational force on Johnny is going to be 500 over 6. And I'm feeling a bit lazy right now to do that math. Finally, if he's in outer space, where there is no planet to act on him, the gravitational force is going to be 0. So you see that the gravitational force, or the weight of an object, is actually the interaction between the object and the gravitational field of the place. And because it is an interaction, it's something external to the object, and it will change. It changes as gravity changes. So the weight of an object will change as you go from place to place. And let's remember that weight, being a force, is measured in newtons. Well, I hope you enjoyed this video about Newton's second law and that you could understand the video. In a sequence, we have a screencast with several problems that will help us better understand the concepts and how to apply what we just learned. See you around.